Hi everyone, welcome to questions on dynamic equilibrium. The first question we have is asking us a closed system is required for dynamic equilibrium to be established. State one other feature of this dynamic equilibrium. So there's a few features of a system that's in dynamic equilibrium. So you should hopefully know them, like only a few you need to know about. One of them being a closed system. Other ones we're looking for is your forward reaction is equal to the reverse reaction, or you're saying they both occur at the same rate, and the concentration of your reactants and products does not change. They'll be consistent because it's a closed system, so you're not adding or taking anything away. Once dynamic equilibrium is set up, it's all running smoothly. Those are the situations we have there. So any of those will be absolutely fine. Any of those two will be fine. Okay, next one, we're talking about heating the equilibrium mixture. And then it's asking us how the equilibrium mixture is going to change upon heating. 2 marks. Now, when it comes to heating, you need to just be aware of whatever this is here. So they'll most likely give you the delta H value. If not, they might give you some other information, but generally they tend to put that on there for you. So that's telling us that the forward reaction, doesn't know anything about the reverse reaction, the forward reaction is exothermic because it has a negative value there. Now the actual number itself doesn't matter, that's irrelevant really in terms of this question. It's just the sign that's important. So the fact that it's a negative charge there tells us the forward reaction is exothermic. So if we heat it, so we're increasing the temperature, then that's going to favour the endothermic direction. So therefore the equilibrium is going to shift to the left hand side. It's going to shift towards the reactants, the H2 and the I2, so that's not really ideal. So we can say more H2 and I2, or you can say less HI, which is our product, whichever one you want to go for, the other way around, it'd be fine. And then also then saying where the equilibrium shifts towards. So equilibrium shifts to the left because the forward reaction is exothermic, or you say the reverse is endo. So you've got to put those in. Just make sure you're ticking all the boxes there in that regard. So as long as we've got both those in there, be absolutely fine. So you can say what you get more or less of, and then you've got to give a reason as to why. It does say explain your answer, so you've got to put your reasoning in there. Okay, following on from that, it's asking us what effect would increasing the pressure have on the position of equilibrium. So again, just, you never know, heat at the moment, you might suddenly panic and forget what you're writing about. Increasing the pressure. So for this one here, we just need, for anything to do with pressure of the equilibrium, we need to count how much of everything we have on each side of the arrows. So we want to look at the big numbers in front of our reactants and our products as well. So we can see we don't have a number in front of our H2 and our I2, so that means there's effectively a 1 there. We have 1 for H2, 1 for I2, we've got 2 lots of HI. So we've got 2 lots, we have 1 plus 1 gives us 2 on the left hand side, and we have 2 on the right hand side. So we have the same amounts on both sides. There's not more on one side and more on the other side. So increasing the pressure will have no effect. Because normally if you increase the pressure, equilibrium will shift to the side that has fewer. If you decrease the pressure, it shifts to the side that has more. So, but in this instance, because both sides are the same, it's 2 on each side, therefore it will have no effect. Got the same number of everything there. So, with the effect, there'll be no effect, and you've got the same number of moles on both sides, or same number of molecules, however you want to say it. Okay, final question, quite a big question, 5 marks here. We've got our equilibrium set up there, giving some information about it. We need to explain your prediction in terms of, so we predict the conditions of temperature and pressure for maximum yield. So that's what we're aiming for there, maximum equilibrium yield of nitrogen monoxide. So we'll just, again, so we know what we're trying to answer in this question. Maximum yield of nitrogen monoxide, sorry, which in the equation is there. Again, if it was me, I would just highlight that as well. That's going to be important. So we need to explain your prediction in terms of Le Chatelier's principle, state and explain how these conditions could be changed to achieve a compromise between equilibrium, yield, rate, and other operational factors. Okay, so again, I'm just going to highlight yield, rate, and then operational factors, which we'll get to. So we need to mention all of these things here to get 5 marks. So let's start off with temperature. So looking at this, we know that the forward reaction is exothermic, as we've got that negative delta H value there. So increasing the temperature isn't going to be ideal, because if we increase the temperature, it's going to go to the reverse reaction. So it's going to go towards favour our reactants. But we don't want to necessarily lower the temperature too much, because then it's going to be a really slow reaction, because increasing the temperature, we're going to increase the kinetic energy of the molecules, so therefore get a faster reaction. So again, this is where we're going to go into the compromise in a little bit. So we need mentioning something about that. So in the forward reaction is exothermic. I mentioned delta H is negative. Something along those lines. That would be a good thing to mention. The pressure, well, again, we need to add up what moles we have on each side. Left hand side, we have 4. Just because we can see. So we've got 4 there. We've got 5 there. We've got 4 there. And we have 6 there. So we've got 5 plus 4 is 9 on the left, and we've got 4 plus 6, that's 10 on the right. So we have more molecules on the right hand side on the products than we do on the left hand side. So that therefore means ideally we want to increase the pressure. Sorry, no we don't. We want to decrease the pressure, because then we'll shift to the side that has more molecules, which would be the right hand side. So ideally we'll decrease the pressure. That's good because it's cheaper, because obviously creating high pressure is quite a difficult thing to achieve. It's very expensive to achieve. And the issue also, if we lower the pressure, then the reaction again would be quite slow, which again we don't want to be wasting time hanging around waiting for this to happen. So mentioning left hand side has fewer, or the right hand side has more, mentioning some numbers 9 and 10, we all good. So these optimal conditions, I've mentioned this, talking about temperature and pressure. I've broken this down into separate sections. Obviously you could put it all in the one answer if you wanted to. So I've mentioned equilibrium conditions or optimizing them. So what we'd ideally like, we'd want a low temperature, I want a low pressure, because then equilibrium will shift to the right hand side and then favour our products, which is what we want. But then the issue we have with that is that it'll take quite a while. So that's why I mentioned the rate. So we're mentioning yield, so it mentioned the equilibrium yield, so we mentioned that. And then we're talking about the rate. Well, as we say, low temperature, low pressure will give us a low rate. So we need to maybe increase temperature a little bit and also the pressure a little bit, just so then we get the reaction going and it's actually somewhat speedy in a sense. Now there's other industrial conditions / operational factors. Now this is something that they can throw in there just to see if you can handle it. And all we've got to do is talk about the things mentioned in the question. So pressure. High pressure, well, it's expensive for one, and it will reduce the yield, so that's not ideal. And also your high temperature as well. So very high temperatures and very high pressures, although they're ideal for this particular reaction, it could potentially be dangerous. Having things at very high temperature and pressure, something goes wrong, then that's not ideal. And obviously, like I mentioned before, it can be very expensive as well. So all those things there, 5 marks. Maybe the operational factors could be a bit of a sticking point, so you might drop a mark there, but the other ones I think could be fairly reasonable to pick up. Okay, so that will do us for today on questions with dynamic equilibrium. See you next time.